Hello and welcome to ShellShock Live. Today I'll be doing something very different from previous videos, and I'll be using physics and math to create the ultimate calculator and the ultimate cheat in this game. So, if we go into the fire range, what we can do is we can take advantage of the fact that this game is very deterministic. There is very little RNG involved. So if I shoot the exact same shot, the exact same way, 2 times in a row, it'll follow the exact same path every single time. Now, we can then come up with a formula to figure out, given a certain power and an angle, where will that shot land? And then, with that formula, we can backtrack and say, given a certain position, what power and what angle do we need to fire at to hit that position? Now, as you can see, this can be very powerful if we're playing any sorts of game. We can say, man, I can measure the distance between these two places and say, oh, I want to shoot right there, I want to kill that opponent, and get my calculator out, calculate, boom, and hit it perfectly. And I missed because I'm not using my calculator and I'm kind of bad at this game, so I will be showing the math. Now, how do we apply physics in this situation, you might ask? Well, we can measure two things. We don't know the acceleration of gravity on this world yet, but we can measure distances. We can measure distances in pixels, and we can measure time intervals using video editor software. So what I did before this is I went on a flat map and I shot straight up with 77 power. And you can see that it reaches a certain maximum height and takes a certain time to get there. Now you can measure the height in image editing software, and you can measure the time it takes using video editing software. And then using physics equations, you can determine the acceleration of gravity in pixels per second squared. Now, once you have gravity, then you can figure out, what does 100 power mean? What do velocities mean? Because you don't know what 100 power means. It could mean 100 pixels per second, it could mean something else, you don't really know. So then, using gravitational constant and this measurement, and how long it takes, then you can figure out velocities in the game. And then once there, you can use more physics to find out the ultimate calculator. Now let's get to the results. Okay, so here we are trying to solve for the gravitational constant with actual measurements. Now here are the measurements that I got. So from rest, it took 1.23 seconds to fall 427 pixels, and also from rest, it took 0.67 seconds to fall 107 pixels, and it took 1.983 seconds to fall 1,000 pixels. Now, we know that the acceleration of our object going down is only affected by gravity, so our acceleration is equal to g, our gravitational constant, which is what we're solving for. Now, when we integrate acceleration, we get velocity, and when we integrate g with respect to time, we get g times t. Then when we integrate again, we integrate velocity, and we get x, and we integrate gt with respect to time, and we get 1/2 gt squared. And there are some constants here that you might recognize from other physics equations, but since our initial velocity is 0, we're going from rest, those constants go away. Now, we have x equals 1/2 gt squared, and if we solve for g, we get g equals 2x over t squared. Now, plugging in our measurements, when we have our time is in this column, and our x is in this column, we can do the 3 different measurements of the gravitational acceleration. So for our first trial, 2 times 427 over 1.283 squared, we get 518.8 pixels per second squared, so that's our g. But we try it with another measurement, and we get 467, which is somewhat different. And then if we do it with the biggest one, we get 508.61 pixels per second squared. Now, because I was analyzing it with frame by frame, and the frames were not like 0.001 seconds apart, they're significantly apart, I'm trusting the bigger measurement more because there's more, the margin of error is small relative to the biggest size. And also, since this 508 is between 467 and 518, I'm most inclined to use 508.61 pixels per second squared as our gravitational constant. So our next task is to find out what power means and to be able to measure velocities. Last time we were looking at accelerations and gravitational constant. Now we can use that to figure out velocities and what power means. So before, when I was measuring the distances and the times, what we had is a tank that was shooting straight up. I showed you in the gameplay with an initial velocity v0, which we can be measured in power. Then it went up to the top and it came to a resting point where it turned around in velocity as it was at rest, and then it fell all the way down. And before, what we were doing is we were measuring this distance and the time it took and then figuring gravity from that. But now we can use the symmetrical properties of parabola. Since a parabola looks like this, our parabola is just super skinny. It's straight up and down like this. But over time, it looks like a parabola. And because it's symmetrical, we know that the velocity at the same height going up is the same as the velocity going down, just in the opposite direction. So we know that when it reaches the ground, its velocity will just be the same as the power that it went up with, but going down, obviously. Now we can use the physics equation V equals AT, and this is derived from the fact that A is just a constant, and if acceleration is constant, then if you multiply it by time, you get velocity. I mean, if you have pixels per second squared and you multiply it by seconds, you should get pixels per second, which is a unit of velocity. And then we can use the fact from last time that our acceleration is equal to gravity, which equals to 508.61. Remember, we had v equals gt in the last one. This is the exact same thing as that. It's just a, which is actually g. So we have 508.61 pixels per second squared is our gravitational, and then we can just plug that in for a, and our time we already knew was 1.983 seconds. I'm using the biggest measurement from last time because that was the most reliable. So our velocity is equal to 508.61 times pixels per second squared times 1.983 seconds, and we get 1008.574 pixels per second. And we know this is a downward velocity, and that should equal to 77 power. And then if you divide 1008 by 77, you get 13.09 pixels per second equals 1 power. So now we have a method of converting power to pixels per second, and pixels is what we're going to be measuring everything in for the rest of the video. Okay, so now that we have our g, our gravitational constant, and we know how to translate powers into velocities and velocities into power, we're ready to tackle our final problem, which is, given a position, what power, what angle do we shoot our projectile at so that it hits that position? So you can see from our diagram here, this dot, this is our tank, it's 0, 0, and this is our v0, our initial velocity, and this angle is our theta. And then the point we're shooting at has an x component of A and a y component of B. So how will we tackle this problem? Well, we can find the equation of the parabola the projectile arcs through, and then we can find the equation of the line that goes through that point, and then find the intersection point. And this will give us an equation in terms of A and B, and v0 and theta, and then we'll be able to solve for anything we want. You'll see that later, and then we can calculate all sorts of things. It's crazy. Okay, but first we have to go back to this series of integrations that I've been doing every time. So, but I want to make it more general this time. So we have A equals A instead of A equals G. We just, for anything, it could be, yeah, we could have A equals 0. So if we integrate this, we get V equals AT plus VI. Now before I said there were constants that we didn't have to worry about. Now that we do have an initial velocity, we do have to worry about these constants. Before it was from rest, now it's not. So our velocity equals our acceleration times time plus VI. And then we integrate a second time, we get a position. Before it was x, the reason I wrote position here is because we're using x over here. I don't want to confuse you. So we have our position equals 1/2 AT squared. Before that was 1/2 GT squared, but we want to keep it general. And then we have these constant terms. We integrate the VI and we get VIT. And then we also have our second constant because we integrated 2 times. And we have our XI, which is our initial position. Fortunately, our initial position for both the X and Y is 0. So we do not have to worry about that one, but we do have to worry about the initial velocity one. Okay, so first, the simple one, the really easy one, the equation of the line. We want a line that goes through 0, 0, and AB. Well, the slope of this line will be b over a, rise over run, and it has a y-intercept of 0, so there you go. Slope-intercept y equals b over a times x. Simple enough. Now, the parabola is a lot more complicated. And the first thing you need to know is that because our force is only acting in one direction, we can break down our velocities into two components, two independent components, two independent perpendicular components. Got that? Okay. So we have our vertical component that is acting independently of our velocity. It's kind of weird if you think about it the first time you think about it. But we have gravity that is only going downwards. And then that means, since gravity is only affecting downwards, the horizontal velocity remains unchanged. So it'll be constant. It'll be going along. Gravity doesn't affect me, no matter. But the height is affected by gravity. Okay, so this concept is slightly weird, but in order to do this, this vertical and horizontal component, we have to break down our initial velocity into vertical and horizontal component, which is what we have over here, our triangle. So this is a right angle triangle. We have our V naught as the hypotenuse and theta is the angle here. And you just do some trigonometry. You get the height is V0 sine theta and the base is V0 cosine theta. So now the equation of the parabola. We will have two independent equations that depend on time, which is weird. And this is where this will come in. Okay? So ignore this y for a second. First, we just want x. This is our horizontal component. Now, for our horizontal component, gravity, there's no acceleration this way. There's only acceleration this way. So our x component has 0 acceleration. So a equals 0. So our position equals 1/2 at squared plus v initial t. Well, guess what? A for x for our horizontal component is 0. So this term goes away for our horizontal. But our initial velocity is not 0. Our initial velocity for the horizontal component is v0 cosine theta. So you can plug that in for v initial, and then you multiply by t, and you get this equation: x equals v0 cosine theta t. So this is what's called a parametric equation. We have a y and an x in terms of t, and then we can combine later to create an equation of parabola. Okay. So this is the easier one. Now we have y, and this will be going up and down and affected by gravity, okay? But it's familiar from before. We know our acceleration is g, and so we can do the same thing. Position equals 1/2 gt squared plus our initial velocity t. But there's a caveat. Before we were loosey-goosey with our signs. Now we have to make sure that gravity is going downwards. It is making our y less and less. So that's why this 1/2 gt squared is negative, because our acceleration is actually negative g, because we're treating up as positive. But this other term, v initial times t, is just v0 sine theta times t. It's the same as this, except with our vertical component, and then we have this other term that's a result of our acceleration, which is negative 1/2 gt squared, because our acceleration is negative g. Okay, so now we have an equation of parabola and we have an equation of line, but these don't really match because we have t's, and we need to get rid of the t's first. Okay, so we're starting with our parametric equations: y equals v0 sine theta t minus 1/2 gt squared, and x equals v0 v naught cosine theta t. So how are we going to get rid of t? Substitution. So we take x equals v naught cosine theta t, and we solve for t. We just divide both sides by v naught cosine theta t, and we get t equals x over v naught cosine theta. Then we just plug in this for t into this equation. So every time we see t, we instead put x, and we'll just get rid of t's, and we'll have x's instead of t's. Okay. So you have y equals v naught sine theta times t, but this t is now x over v naught cosine theta, and then 1 minus 1/2 gt squared, but t is actually x over v naught cosine theta, and then we just square it. Okay? So we can do a little cancellation here. We have a v naught on the top and a v naught on the bottom. We can cancel those. And sine over cosine, opposite over adjacent, is just tangent. So we have tangent theta times x minus and we do a little rearranging. We square everything in there, and we get g over 2 v naught squared cosine squared theta times x squared. So if you'll notice, y equals this. This is y equals x. This looks like a quadratic equation. We have y equals something x squared. Notice we don't have a constant term because our y-intercept is 0. Remember, we said our initial position is 0. If we plug in x equals 0, we should get 0, which is what we do. So now we have to go back and we have to solve for our intersection point. And we have, remember back, we had the equation of line b over ax, and we just set that equal to this. We said the first y equals the second y, and yeah, there you go. So b over a times x equals tangent theta x minus g blah 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 blah. Notice that this has an x, this has an x, that has an x squared. We can divide by x. Now this eliminates the solution x equals 0. If we put in x for, we've put 0 for x everywhere, we get a valid solution. And this is true because there's two intersection points into that between the equation and line. If you remember, over here, there's an intersection point at this, and there's also an intersection point at the point AB. We're only interested in the point at the point AB, so we don't have to worry about this, and we can say we can divide by x. We won't be dividing by 0. Okay, that's the way. So b over a equals tangent theta minus g over 2 v naught squared cosine squared theta times x. Now, at the solution point, we know that our x will equal a. Because in that parabola, our x distance will equal a. So then we plug in that, and we get b over a equals tangent theta minus g times, now our x is a, g times a over 2 v naught squared cosine squared theta. Now it's just algebra land, and we want to solve for something. We don't know. Do we want to solve for our velocity? Do we want to solve for theta? Do we want to solve for a, for b? There's a lot of variables going. What are we trying to solve for? Well, it's because we can solve for anything, really. that's the answer. But what's useful to our problem? Well, usually we know our angle that we're shooting at, and we want to figure out what power gets us to the right position. Or we could do the other way. We could say, given a certain power, we want to shoot at 70 power. What angle do we shoot at to get to our position? Well, I think it's easier to know what angle you're at, because maybe there's a bumper in the way, or maybe there's a hill in the way, or maybe there's a black hole in the way. So usually you want to avoid a certain angle, and you'll know your specific angle, and then you'll see what power to adjust. So what we want to do is we want to solve for v naught from this. And now that's just algebra. Okay, so we're starting with b over a equals tangent theta minus ga over 2 v naught squared cosine squared theta, and we're solving for v naught. Just rearrange, add this term to both sides, subtract b over a, we get that equation. Then we multiply both sides by this term, 2 v naught squared cosine squared theta. We divide by tangent theta minus b over a, and then we bring the g over to the other side, and we get a over tangent theta minus b over a equals 2 v naught squared cosine squared theta over g. Then we bring the g back over, we bring the 2 and the cosine squared back over, square root, and we get the square root of g times a over 2 cosine squared theta times the quantity tangent theta minus b over a equals our v naught. So we have our a and our b, we give it an a and a b, which is our position we want to reach. We give it a theta, which was the angle we want to use, and it'll spit us out a velocity, a power. Now this will give us a velocity in terms of pixels, and actually in the game we want to multiply by 13.09, sorry, divide by 13.09 to give us the number of power. But then, yes, so now I'll put this all into Desmos, and we can see a nice graphical interpretation of this. Okay, so right now we have the basic range equation. You can see from this origin point, we have a parabola. We can change our initial power, and we can change the angle at which we shoot it from. with these fancy sliders. Now you can see here that this is the equation of that parabola, that first parabola we had. P is just theta, and we multiply by our velocity by 13.09 so that we can use this nice slider from 0 to 100 for ease when we're doing the actual in-game calculation. But the rest here, you can see g times x squared, 2 times, this is all what we had. But this is just to see the basic behavior of the parabola. You can see that 45 degrees is the optimum distance angle. But now we want to get to the fancy part. We want to get to the part that goes through a certain point. And that is this junk over here. So our V0 is dependent on A, B, theta, and theta, P. And we have our gravitational constant, which is 508.61. And we have an arbitrary A and an arbitrary B, and we have an arbitrary theta. So this includes down points. And now we can drag this point. So this is our, if this is our position of our tank, this is the position of the enemy position, the enemy tank, in pixels. So if it's 600 pixels away, like this, then this is, and our angle is 34 degrees. We want to shoot it with a velocity of 43.84. Of course, we can only do increments of, we can only do whole numbers. We can only either do 43 power or 44 power. But yeah, that would be the perfect shot. And you can just drag this around. You can change the angle at which you shoot it at. If we want to avoid a black hole that's right here, we can increase the thing and change which point we're shooting at. And now we can actually go into the game and do some actual accurate calculations. And you can see the behavior of the function. It's just fun playing around with this stuff. Going side to side, going up and down. It's really fun. Anyway, so yeah, now we'll actually put our stuff to the test. See if this 508.61 is a thing. See if our calculations are correct. We'll be using this velocity and this angle to be making our in-game calculations. Okay, so this footage is sped 5 times up, partly because the frame rate was at like 10 FPS, and also because it's kind of boring footage. But here we are. This is just me doing some calculations, and there's adjusting the power, and we should get a perfect shot, 170 damage. This is the mission where you have to get about 10 shots perfectly in a row, and I was not about that. I'm not good enough, so I decided to make this calculator for that. So this is me measuring the distance, and you can see me adjusting the A and B there. And then I want a high angle because he's close to the wall. And there you go, 62 shot. And here I move away just because the snipe does more damage the further away you are. And also you'll note that I'm measuring from the muzzle of the gun. I figured out that I think was the place where the projectile was spawning. And I'm also adjusting here to find an angle that's close to a whole number, because or a velocity that's close to a whole number, because if I don't do something that's close to a whole number, it might be 0.5 and miss or something. But yeah, just doing this over and over and over. Note that this is sped up. It's going to take a while. I'm not sure if it gets fast enough if you're doing a multiplayer or something. Yeah, if you're doing multiplayer, you're probably going to have to create a ruler on screen and create a pixel to inch conversion and then do it even quicker, like on a separate tab or on your phone or something. You don't have to do the whole measuring out with a screenshot or anything, because that's the part that takes the longest. But yeah, so this is the end of this video. It's gone long enough. I'll let the rest of the footage go out, but I do have many more ideas. I want to do wind. I want to do spiker things, hoverball, boomerang. But this is the first. Want to see how it goes. And yeah, thanks for watching.